Hello everyone, welcome back to our course on memory device technology for AI/ML computing. I'm your instructor Dr. Shubhadeep from IIT Hyderabad. So let's have a very brief recap of what we studied the last time around. We were looking at the program operation of the NAND flash cell, both at the cell level and at the array level. So at the cell level, we saw how the dominant transport mechanism was Fowler-Nordheim tunneling. This is the tunneling which happens through a triangular barrier at sufficiently high gate biases or bias at the control gate of your flash cell. This transport mechanism gave us several advantages such as non-volatile operation both at hold and at read condition, but also it resulted in large biasing requirements and slow program times. Okay. At the array level, we saw how program operation is facilitated at the page level. You see what we had shown. This was the page we were essentially trying to program. Since there are no direct connections to the cell of our interest, this was done in NAND flash. The serial architecture in NAND flash does not have direct connections to our cell of interest. It becomes very important to do very intelligent biasing. Why? Because you see this cell shares the word line and bit line with other cells in the page and in the string respectively. So you do not want unwanted program to happen in places that are not of interest to you or cells of not interest to you. And this you do through intelligent biasing. The most interesting thing was you apply something called the inhibit voltage at cells or at bit lines where you do not want to facilitate program. This increases the channel potential and therefore stops Fowler-Nordheim tunneling to happen, because Fowler-Nordheim tunneling can happen only at large biases, sufficiently large potential differences between the control gate and your channel. Okay. One very important aspect I did not really emphasize in the previous class was to appreciate that during the NAND flash operation, especially program operation, it may not look in this particular diagram that huge amount of data is being programmed, but this is not the case. Please remember, generally in a page, there are close to 64 to 512K bit lines. So at a time, you are programming 64,000 to 512K bits at a time, and this is what makes NAND flash our cell architecture, NAND flash array architecture very, very special. So in today's class, we will continue from here and we will look at erase and then read operation of the NAND flash both at the cell level and also at the array level. So let us begin. So how is the erase operation done? First at the cell level. Let me play this animation again for you. As you can see in this animation, just opposite to the program operation, in the erase operation, electrons are flushed out or pushed out from the floating gate or the charge trap layer into the channel. Okay, so in program operation, electrons were pulled into the floating gate. In erase operation, exactly the opposite happens. Electrons are pushed out of the floating gate. So it should not be very difficult to understand what will happen at the cell level for the erase operation. To do that, for the sake of thoroughness, let's again try to draw the band diagram at the cut line. Remember, the cut line was a cross section across the floating gate terminal, and we will plot the band diagram across this. So remember, one side was your control gate, other side was your p-type substrate. In this case, there are already electrons which are stored at the floating gate. During the erase operation, the idea is to flush out these electrons from the floating gate into the channel, as this particular schematic shows. The question is, what should be the biasing technique in order to facilitate this transition? So in the program operation, if you remember, in order to pull in electrons from the channel, you applied a positive gate bias plus 20 volts at the control gate. However, in erase, you have to push out electrons from the floating gate into the channel. So it is common sense to expect that the band bending when you want to have erase operation has to be opposite to that of the floating gate, and therefore to push out electrons you need to apply a negative 20 volts or minus 20 volts at the control gate, as we have shown over here. Remember, in band diagrams we plot electron energies. The moment we put minus 20 volts at a terminal, you are increasing electron energies, and that is why there is an upward movement of the bands. And just like there was Fowler-Nordheim tunneling, significant amount of Fowler-Nordheim tunneling through the triangular barrier in the program operation, same is the case in erase operation, but just the direction becomes opposite. So all these electrons which were stored here in the floating gate through Fowler-Nordheim tunneling are flushed out into the channel region. Again, it is important to note that by the virtue that the blocking oxide is very, very large, the size of the blocking oxide or the thickness of the blocking oxide is roughly 15 nanometers. Therefore, this prevents any significant Fowler-Nordheim tunneling to happen from the control gate into the floating gate region. So that is prevented. Therefore, there is only kind of one-way traffic or one-way transport of electrons from the floating gate into the channel region. Okay. Now, this is what common sense will suggest to us, that control gate should be programmed. Control gate, there should be an application of minus 20 volts at the control gate. But in reality, in practical devices, this is not exactly what happens. So what exactly happens is, it's not that there is minus 20 volts which is applied to the control gate, but quite the opposite. What happens is, the control gate is biased at 0 volts, but the substrate which is connected to the channel is connected to plus 20 volts. It is the same effect. Instead of having the substrate grounded, you are connecting the substrate to plus 20 volts and you are grounding the control gate. Okay, it has the same effect, but there is a twist in the biasing conditions. This will also cause similar kind of band bending, which will result in the flushing out of electrons from your control gate into your channel through Fowler-Nordheim tunneling. Now the question is, why is this done? In the program operation, the control gate was put to plus 20 volts and the substrate was grounded. Here, why is it reversed in the case of erase? And this is a very important part of flash operation. Remember where this terminology flash came from. The terminology of flash came from the fact that you can do erase operations at the block level. Remember, your program operation was at the page level. So the applying voltage was done, or the facilitating voltage was done at the control gate. Here, the erase operation is done at the block level. How do you facilitate block level erase? You ensure that all the transistors in the block have a common p-type substrate. All the transistors in the block, if they have common p-type substrate, they have one connection which is common to all these transistors from the substrate. And what you can do is, at just one go, you can completely erase the contents of all the cells in the block. Okay, so let us see how that is done at the array level. So as we just discussed, erase operation is done at block level in just a flash, and that is where the name flash comes from, or NAND flash comes from. So how is this done? Like we discussed, there is a common substrate connection. Here we have again represented our block level diagram. Just to recall, our block level diagram consisted of cells organized in pages, which were your vertical word lines, your horizontal word lines, and your strings, which were your vertical common bit lines. But however, since erase is done at the block level, we are not very specifically interested in what is happening at the word lines and bit lines. What we want to ensure is that you just apply zero gate bias at the word lines, and you apply a common bias of plus 20 volts at the substrate. The substrate voltage, as we just discussed, is connected to all the P plus substrate of all the cells in that particular block. Okay, so how is this done? Let's look very quickly at the biasing scheme. The first thing to note is that in the biasing schematic, the source select line and the ground select line are kept at floating condition. Why is the source select line and the ground select line transistors kept at floating conditions? Because you are going to apply a very large bias at the substrate. Now, if you apply a very large bias at the substrate and there is some finite voltage on the gate terminal or even at the drain terminal, there is a chance that this particular transistor, when you see plus 20 volts, it may just break down. So to prevent the breakdown of the source select line transistor and gate select line transistor, it is ensured that the gate terminal and the drain terminal, which are the respective bit lines, all the gate terminal and the drain terminals are kept in floating condition. Then only you can have a plus 20 volts that is applied to the substrate. If you do not apply floating, there will be significant amount of current that can flow through the gate oxide and break the gate oxide of your logic transistors, which are your SSL and GSL transistors. Okay, having said that, let's now look at what will be the biasing condition at the word lines. As we know, all the biasing of the word lines will be zero, because when you do the erase operation, all the transistors in a particular block are erased. So all the word lines or all the pages, which is nothing but connected to individual word lines, are biased to 0 volts. And finally, what is done is the substrate voltage of that particular block, sometimes it is done for multiple blocks also, is also asserted to plus 20 volts. And when you assert plus 20 volts at a substrate and 0 volts at the control gate, all the electrons which were present in the at the floating gate are flushed out into the channel region. Okay, and the operating mechanism, as we saw, or the charge transport mechanism, as we saw in the previous slide, of this ejection from floating gate to the channel is Fowler-Nordheim tunneling, the tunneling through the rectangular barrier. Now, another very important thing to emphasize is, remember that block erase times are generally slightly larger or significantly larger actually compared to read times and program times which happen at the page level. So generally block erase times are at the order of 1 millisecond. So a natural question would be, why are erase times much significantly larger compared to the program times? The reason for that is that when you start doing erase, you are dealing with a lot of cells, right? When you deal with a lot of cells, you can imagine that there will be lot of cell to cell variability also. So there will be cells which are called fast cells, where quickly the Fowler-Nordheim tunneling current can remove all the charges from the floating gate. However, there can also be cells where there may be some defects, due to which they become slow cells. These slow cells take significantly little larger time to do your erase operation, and therefore to account that all the cells, including fast cells and slow cells, have been properly erased with 100% erase efficiency, that is, all the electrons which are there in the floating gate have been effectively ejected out, you ensure that you give it sufficient time. So you give 1 millisecond at the block level of plus 20 volts to ensure this, and therefore the erase times are slightly elongated. Okay, so with this we move on to the read operation. So the read operation is something that we have been discussing for quite some time. The read operation at the cell level should be fairly intuitive to you, but let's go over it. The first step of doing the read operation, or the best way to understand the read operation, is to look at the transfer characteristics of the flash cell, both in erase and program state, and that is what I have done in the ID versus VG curve. Okay, so the first step of doing the read operation is to apply a very tiny small control gate voltage, which is also called the read voltage. We read at the control gate. So what do you mean by applying a small voltage at the control gate? Of course, it means that it should not be any way comparable to the voltages that you apply during program or erase operation. Why? Because if you apply anything close to that, there is a distinct chance that the cell state may get altered. So you keep the control gate much smaller compared to what is required for program operation. So you do not want Fowler-Nordheim tunneling or alteration of this cell program of erase during read. So this is done by selecting a small VRead voltage. This is just the first criteria. The second and the most important criteria is to make sure that the read voltage at the control gate is exactly midway point between the threshold voltage in the program state and the threshold voltage in the erase state. Okay, so in this particular example, we see that the program state, at the program state, which is also the state 0, roughly the threshold voltage is plus 2 volts, whereas in the erase state the threshold voltage is minus 2 volts. Just to remind you, why is the threshold voltage at program state much higher than that in erase state? This is because in the program state there are electrons which are stored in the floating gate of the flash cell. And if there are electrons which are stored in the floating gate of the NAND cell, of course threshold voltage will be much significantly higher, because now the gate bias has to work harder to first remove the accumulated positive charges which were induced by the negative electrons which were trapped in the interface. So first, from accumulation you want to bring to flat band, then from flat band you want to bring to inversion. This is what we had discussed in our first class of NAND flash cell. So if you don't remember, please go and watch that video once again. And similarly, in the erase state, where there are no electrons in the control gate, you would expect that the threshold voltage will be much smaller compared to that in the program state. Okay, so this is the first step you do at the cell level for read operation. You select very intelligently the control gate for read operation, the voltage at the control gate for read operation, which is right in between the threshold voltage for erase state and of program state. So since erase state threshold voltage in this example was minus 2 volts and the threshold voltage for program state was plus 2 volts, we have selected the voltage at the control gate for read operation to be 0 volts. Okay, so at 0 volts, let's see what happens. So the next thing that we do in the read operation is we apply a very tiny drain bias. We apply a tiny drain bias. Why do we do that? Just to check whether the cell is in on state or off state. Of course, because you had selected the threshold, the control gate or the read voltage less than the threshold voltage at program state, in the program state the transistor will be off, and as a result there will not be any current that will flow even if you put a small drain bias. However, in the erase state, because the read voltage was selected such that it is higher than the threshold voltage of the transistor. This transistor in the erase state or this flash cell in the erase state will be in on state. So you will be able to measure a significant amount of read current because the cell is in on state. So this is the read current that you will effectively measure. So this is the very simple mechanism of read operation at the cell level. You select a control gate, small control gate bias, which is in between the threshold voltage of erase and program state. Then you apply a small drain bias to check whether the transistor is on. If it is on, it is in erase state. If it is off, it is in program state. However, as you can understand, when we try to translate the same idea at the array level, we have to again do some intelligent biasing at all the terminals. Why is this the case? Because the read operation is done at the page level. That means one common word line is used when you do the read operation. So just like the program operation, read operation is also done at the page level. And as we had discussed, since the cells that you are trying to read out have common other common transistors or other common cells in the string and in the page, you have to be very careful not to alter the state or not to read out incorrect information from the neighboring cells in the string or other cells in the string. So how is this done? To understand this, let us understand this with a simple example. In this particular example, the first cell and the nth cell we have retained in the erase state, which is state 1. This is just a follow through of the example that we saw in our program lecture. What happens is cell 1 and cell n is still in erase state, but now what has happened is by doing a program operation, you have altered the state of the second cell in the page of our interest. So now the idea is we want to read out that for the page of our interest that cell 1 and cell n are in state 1 or erase state, whereas the cell 2 is in program state. How do we do the biasing protocol so that we can do an effective read out of the states of the different flash cells in that particular page? So the first thing that you can understand is what would be the biasing of the transistors at the source select line and the ground select line. So as we see, this is a major departure from what happened both at the erase level and at the erase operation and also at program operation. Both at program operation and erase operation, you did not want any string current to flow. During program operation and erase operation, you would want only charge transport to happen in the direction from the control gate into the channel or the floating gate into the channel. But this is not what you want in case of read operation. In fact, you do not want any charge transport to happen in this direction from the control gate into the channel and disturb the state of the cells during read operation. What you would want is just a tiny read current to flow along the string to indicate whether the respective cell is in state 1 or state 0 or erase state or program state. And to do that, what you do is you apply a gate bias such that you turn on both the SSL, the source select line transistor, and GSL, which is the the gate select line transistor. This is to allow for string current to flow. Another important thing to notice, in program state, the magnitude of the voltage that were applied at the GSL and SSL were significantly larger. However, in this case, you are applying a tiny voltage of 4 volts only. So a question could be, why are you applying a lower bias at the gate terminal when we do the read operation? And the idea is very simple. It is to control the amount of read current that flows, read current which flows through the string. So to control the string current, you can reduce the voltage at the GSL and SSL. Why would you want to reduce the read current? It is just to reduce power consumption. The next thing that we do is we pre-charge all the bit lines to a very small bias of 0.5 volts. So I hope you are familiar and you recall the terminology that I am using here, which is called pre-charge all the bit lines. This is the terminology I have been using both during SRAM and in DRAM operation. So bit lines are generally pre-charged. The meaning of pre-charge is that these cells, the bit line and the corresponding cells, have a large capacitance along with the resistance. So that is why this word pre-charge is being used. It is just similar to what happens in SRAM and DRAM. So first what you do is you apply a small voltage of bit line on this of 0.5 volts on each of the bit lines. So what happens when you apply this small bias? The idea is that it will reach the drain of the cells that you want to read out, and this will provide a small drain bias to eventually read the read current, or to eventually detect the read current from the outside peripheral circuitry. Finally, what is done is you apply the read bias at the control gate of the page of your interest. So the page of our interest is here marked out in dotted lines. Only for the word line of the page of our interest, you apply the read bias at the control gate or at the word line, or as we saw in the previous slide, it was 0 volts because the program state threshold voltage was plus 2 volts, whereas the erase state was minus 2 volts. So in between that is 0 volts. That is what you apply at the terminal of the control gate. However, you have to understand that you cannot leave the other word lines floating. You have to apply a small bias at the other word lines to facilitate this small read current to flow through this string. Because you want read current to flow through the string, you have to ensure that you turn on the flash cells of the page which are not of your interest. So interesting question to ask, which we will cover in the next class also, but you can also think about is, how is the pass voltage during read operation determined? If you think very carefully about it, I am giving you a hint. The pass voltage has to ensure that irrespective of the state of these cells which are not of our interest, the read current is allowed to flow through. So think about it. What should be the pass voltage to be applied to other strings? What is the, so please think about it. What should be the pass voltage applied to other pages or other word lines? How do we determine that? Okay, so after all these biasing protocols are completed, let us try to understand how the read operation finally happens. So just let's recall that cell 1 and cell n were in the erase state or in state 1. So when you apply a small bias 0.5 volts at bit line and you ensure that the other cells allow this bias to get transferred to the drain, what will happen? There will be a effective string current. Why will there be an effective string current in string 1 and string n? This is because, as we had seen, that the read voltage at the control gate was selected such that it is greater than the threshold voltage of your cells at erase state. That means these will cells will be in on state under the current biasing conditions, and there will be a read current which will flow along the string or along the respective string. When the read current flows along the respective string, it is natural to expect that there will be a discharge of the bit line from 0.5 volts to 0.5 minus delta V for both for string number 1 and string number n, and this discharge of the bit line will be detected by the sense amplifier, and we will know that for the page of our interest, the respective strings, the cell is in erase state or in state 1. Please try to recall, because there will be no flow of electrons from the control gate to the channel during read operation. That is how you have designed the read operation. This will be essentially a non-destructive read, or it will be a non-disturb read. Second, since the cell in string 2 is in program state, therefore the respective cell will be in off condition. Since the respective cell is in off condition, it will not allow any read current to flow through this particular string. It will block the read current in this particular string, and therefore there will be no discharge of the bit line in the second string, and as a result the sense amplifier in the external circuitry will read out a 0. Okay, one important thing to understand is that in modern day NAND flashes, the length of each string or the number of word lines pertaining to each string is very large. So this causes huge amount of parasitics, and this effectively slows down your read operation to roughly 10 to 100 microseconds per page. So this is the price that you have to pay for having large integration density. But let me remind you, just like in program operation, read operation also, you are reading out almost 64K to 128K bits at a time, because because this page consists of so large number of bit lines, and therefore large number of bits that can be read out. Thank you very much. I hope you had a good time understanding the fundamentals of program, read and erase operation both at the cell level and at the array level. In the next class, we will try to see the bit scaling aspect of NAND flash. Thank you very much. See you in the next class.